What the heck?
Trigon.
Okay, so in this video regarding Euler's formula, I'm going to demonstrate how you can get the complex exponential representations of the very familiar trigonometric functions. And this video is going to be the part that really helps us get to the hyperbolic functions in the next installment, because having complex ways of representing the trigonometric functions will make it easier for us to figure out what they equal when you put in complex arguments as opposed to just real arguments, and then we can use the angle sum formulas with those complex arguments to then extract the hyperbolic functions out of that. So this is the final jumping off point to then get us to hyperbolic functions in the next video. So here we go. So remember, we've proven that e to the I theta is equal to the cosine of theta plus I times the sine of theta. And we proved that e to the minus I theta is very simply just the complex conjugate of this number. So we get cosine of theta minus I times the sine of theta. But look, we have a system of two equations. One variable, but we have a system of two equations. And if we just imagine adding these two things together, notice that we've got these two things are negatives of each other. So they'll just cancel, right? So why not try that? Let's add these two things together. Because these are equal to these things, adding them will give us the same thing as adding those, so adding these together, they don't really combine very well additively, but we can still just write e to the I theta plus e to the minus I theta. And when we add two cosines together, we get 2 times the cosine of theta. And when we add positive I sine of theta to negative I sine of theta, guess what we get? 0. Big fat 0. It cancels out completely, which means we can derive this. I'm still in awe that this is actually true, honestly, from first learning about it in high school, that this was actually the case, and that's going on 5-6 years ago since I was last in high school. We can just divide by 2. 2 is not 0. You can divide by it all day long. If we divide both sides by 2, look what we get. We get this very strange, complex, exponential version of the cosine function. Really weird. In the context of real numbers, this periodic function can be represented in terms of all complex numbers as its domain as this strange amalgamation of complex exponentials. And this is a true relationship. This is true for every single theta, complex or otherwise. And it's just absolutely stunning. And it's probably not too difficult to see that we can sort of derive one for sine as well. And so I'm just going to erase this, and I'll rewrite it after I prove this one, but just keep this beautiful relationship in mind. Because all we have to do now to sort of get the representation for sine is, instead of adding, we simply subtract. Right? And so we'll get e to the I theta minus e to the negative I theta equals, okay, cosine minus cosine is 0, but minus negative I sine is plus I sine of theta. On the right side of the equation, we get 2 times I times the sine of theta, which means to get to sine of theta, we just have to divide it by 2i. 2i isn't 0, so we can divide by 2i all day long. And would you look at that? We get our very own complex exponential version of the sine function. Isn't that just strange? That's just weird looking. How is this so familiar periodic function in the real numbers equal to something so strange? And of course, this simplifies down to whatever sine value you want when you plug in only real numbers, right? Plugging in real numbers to this, using Euler's formula, by the way, to evaluate these, you will just get, still going through puberty at 23 years old apparently, you will get the sine function out. But this allows you to explore the values outside of the real numbers. And it's just lovely. I mean, look at it. It's so, no pun intended, because it's the sine function, but this is just odd. Couldn't help myself. The pun was totally intended. It's just strange. I mean, look at that. Just kind of appreciate that for a second. It seems spurious. The relationship that trigonometry and exponentials have with each other through the complex numbers seems completely unfounded and spurious. Yet we can prove it in 30 minutes in a couple of videos. It's just lovely. So we have now these two awesome representations from Euler's formula. So from the fact that we know that e to the I theta is equal to, well, we can actually write it like this as a double explanation. We know that e to the plus or minus I theta is equal to cosine of theta plus or minus I times the sine of theta, right? When this is positive, and when this is negative, right? This is sort of the total Euler's formula, right, for negative ones as well. But of course, the sine of theta we know can be negative, so it doesn't really matter if we explicitly write the negative part. But because we know that both of those things are true, we've derived that the cosine of theta is equal to e to the I theta plus e to the minus I theta over 2. And we've derived that the sine of theta is equal to e to the I theta minus e to the negative I theta over 2. And this will hold for all of the relationships. If you square this and add them together, you will get 1. If you take the derivative of this, you will get this. If you take the derivative of this, you will get the negative of this one. It's just truly fantastic. Of course, naturally, we can use these to define all of the other 4 trigonometric functions, right? The tangent function is just sine divided by cosine. So we can take this and divide it by this and get a complex exponential representation for the tangent function that works for all complex numbers. So we know that the tangent of theta is equal to the sine of theta divided by the cosine of theta, which is equal to sine of theta, e to the I theta minus e to the minus I theta over 2i, divided by the cosine, which is the same as multiplying by the reciprocal. So I'm just going to multiply by 2 over e to the I theta plus e to the minus I theta. The 2's will cancel, and we'll be left with e to the I theta minus e to the minus I theta divided by I, right, that I is still staying there, times e to the I theta plus e to the minus I theta. And this is our complex exponential representation of the tangent function. Isn't that lovely? I mean, it's kind of cluttered. It's the best thing that we've got with regards to putting it in terms of complex exponentials. And naturally, the cosecant function, which is just 1 over the sine, is simply the reciprocal of this fraction, right? Cosecant is just 2 divided by e to the I theta minus e to the negative I theta. And the secant function, which is just the reciprocal of cosine, is equal to... Oops, sorry, I made an error. Before, I should have written an I there, right? Sine is this stuff divided by 2i, right? Because it has an I on it in Euler's formula, so when you solve for it, you have to divide by 2i. I apologize for that mistake. The reciprocal of sine is cosecant, and so the cosecant function, in terms of complex exponentials, is just 2i divided by e to the I theta minus e to the negative I theta. The secant function, which is the reciprocal of the cosine function, is just 2 divided by e to the I theta plus e to the negative I theta. The cotangent function, which is the reciprocal of the tangent function, is simply the reciprocal of this. So it would be I times e to the I theta plus negative I theta divided by e to the I theta minus e to the negative I theta. So if you just reciprocate all 3 of these, you'll get the other 3 trigonometric functions in terms of complex exponentials as well. So I will not go into that. But point is, we have these lovely representations. And it's just such a beautiful subject to explore these little facets of trigonometry in terms of complex numbers, because everything is more fun with complex numbers. So I never erased it, but it's at the top of the board. This is all because we were able to prove Euler's formula, which is, well, officially the positive version of this relationship right here. But the point is, it's absolutely lovely. Just stunning. So now that we've covered a bunch of facts in this video, I'd like to save the derivation of the hyperbolic trigonometric functions for the next one. We're not just going to do what's usually said to derive them, which is sort of just sweeping something away from all of these functions. We're actually going to see where you might actually have them pop out of the math, and why you might care what they are in that instance. So we're going to call it quits for today. Thank you very much for watching. This has been the second video that I've made on Euler's formula, and I will be making a third one to follow up. The proof is going out in 2 parts, of course, as you will know, because this won't be getting uploaded until after that. But I'm really, really looking forward to finally exploring the world of complex exponentials more and more than I was before, because anytime I ever referenced them, like in my wacky integral videos, I sort of just declared what those values were, but now I'm really covering what they actually are. So I appreciate those who are watching. Thank you very much for your attention, and I'll see you in the next video. I have an Instagram page for the channel. It is at what the hectagon, of course, spelled correctly, unlike my email, right? Hectagon I spelled in the email with an A here when in fact it's an O. What the hectagon on Instagram. So this is Instagram. I post channel updates there. I also am doing a lot more reading than I used to now, so I'm posting books that I'm reading that I recommend to people. I have a collection of vinyl records that I like to share. Follow me at What the Hectagon on Instagram. I'd like to point out that one of my best friends, who is very much into Dungeons & Dragons, has a YouTube channel called Marching West. He does like a little podcast about Dungeons & Dragons. He does Dungeons & Dragons all the time through his Discord server. He's very, very into it, and I'm sure he would appreciate a bit of a mention. So if you're into Dungeons & Dragons, visit his YouTube channel, Marching West. He also has an Instagram account, again, at Marching West. Also, this fellow, Bill, and I are starting another YouTube channel. I guess you could call it personal reasons, even though it's just kind of funny, is called Fredwood Live. On YouTube, we're just called Fredwood. It's an amalgamation of two different things that were sort of important to us in our college days, which are getting farther and farther behind us. So this is, again, YouTube. We have a channel called Fredwood. We're going to do kind of silly, just us riffing off of each other vlogs that we edit together in humorous ways. But we're also going to start doing weekly video game streams on Mixer. And on Mixer, our name is Fredwood Live. So if you want to see two kind of dopey former college students do kind of ridiculous video game streams and also other things that we're going to do on top of that on Mixer, our username is Fredwood Live, so check us out. Likewise, we have a Twitter account to promote it, also at Fredwood Live. So I apologize for all of these different promotions. I figured I'd just start putting these out there. So there's a few that I'd like you to check out if you're interested. Is my Instagram account, What the Hectagon. On YouTube, my buddy Bill's channel, Marching West. It has to do with podcasts and the like relating to Dungeons & Dragons. The Instagram account for channel updates for that channel. Our joint channel, Fredwood, where we're going to be posting stream clips and vlogs that we make, which are not in any way intended to be serious. It's all supposed to be just kind of humorous. We're going to stream on Mixer because that's the only way that we can use the camera that we have on my Xbox One, and we're not about to buy a Kinect to do on Twitch. So Mixer, Fredwood Live, and the Twitter account for that is at Fredwood Live. So if you're interested in any of these things, please give us a follow. I really appreciate it.